so I will be actually talking about Hawking radiation throughout all these 2 lectures. And I will do my best to derive it for you from the first principles, aiming to phrase as many as possible hidden assumptions and loopholes in the derivation. Of course, I will share with you my way of finding it. And unfortunately, it's not a textbook stuff. It's quite hard calculation, but I will skip all the main, how you call it? Some of the technical details I will skip, but I will phrase how to obtain one or another thing. It's not very hard at the same time. I mean, okay, you'll see. Unfortunately, there is no good reference where one can find a proper derivation of the Hawking radiation because the proper one I find is the one where you can phrase exactly in which approximation you are working and how to find corrections to the calculation. And that's a problem for the most simple calculations. So this is the reference I will use. This is my paper. Unfortunately, it's not very easy to read. It's not a, how you call it, pedagogical one. And it actually contains more than the derivation of the Hawking radiation. It contains also calculation of the corrections to the Hawking radiation. Okay, anyway, so what's the idea of Hawking radiation? The idea of Hawking radiation is as follows. You have a star. Until moment of time t equals to 0, there is non-zero pressure. So before this moment of time, pressure is not 0. And the star is stable. At the moment t equals to 0, pressure drops down to 0, and the collapse starts. So this object starts to collapse. And during this collapse, there happens amplification of 0-point fluctuations. Of 0-point fluctuations. Due to these amplifications, we find non-zero flux. So the expectation value of an operator of the stress energy tensor, I will define these quantities, is not 0, and thermal. It means that there is a radial flux of radiation coming out from here. This is the derivation I will follow for you, sketching main assumptions and the details. Many of you heard the standard explanation that there is a horizon, near the horizon pairs are created, and one of the member of the pair goes down the black hole, another goes out to infinity, and that's how you find the flux. I don't know any, how you call it, trustful derivation from first principles of these calculations. Moreover, this calculation cannot be extended, so you don't really understand how to calculate corrections to this calculation. And usually people bear in mind for these calculations the idea that in electric field you have similar situation. In strong electric field also pairs created. One of the members of the pair goes to that side, so it's negatively charged particles, and positively charged particles goes in that direction, and you also have a flux current in this case, and also flux of stress energy tensor. You also have this in this case. So for this derivation, for this process, I know the derivation, and I can give you how to derive this, and also how to calculate corrections to this situation. But in this case, I don't know. Well, I know, but it doesn't stand any counterarguments, any reasonable counterarguments. So let us discuss what's going on. So I will describe for you the background. The idea is the following. So the background is as follows. I can do the calculation also for this situation, but I will do a simpler calculation, simply in the following sense. I will have a thin shell, so it's empty shell. Empty shell. Inside it, there is nothing. It's not a filled-in ball. It's empty shell. So it has delta functional source on the radius r0. Outside of it, it creates the same gravitational field as a ball of the same mass, whatever radius it has. That's probably you know, even since the school time, it's true even in Newton gravity. The same is true in general relativity. So the metric in this case is as follows. It has, it is piecewise defined. Inside the shell, it's flat. So it's dt minus squared minus, what signature I use just to make sure that okay, I use this signature. dr squared minus r squared d omega squared. This is for the r less than rt. I will consider the situation that the shell starts, so at 0 moment of time, it is r0, and then it goes r of t. So there is a collapse. So there was a force, external force, maintaining the shell at this position, and then the force gone, and the collapse starts. So inside the shell, the metric is as follows. Outside the shell, the metric is like this. It's Schwarzschild. So, and I assume that R0 minus R0 is greater than RG, and R0 minus RG is much less than RG. So it started its collapse being very close to the Schwarzschild, its Schwarzschild radius. RG is doubled mass of this body. And I use in the units where Newton constant is 1, C is 1, and H bar is 1.
Sorry, can you repeat? Does the shell have a mass?
Yeah, of course.
Where? In the center?
No, it is itself massive. The shell is massive.
Why the first metric is...
Because inside the shell there is no gravity. It's true in Newton gravity also.
Okay.
If you have a thin shell, inside shell nothing feels the gravity. It's a high school time stuff. Okay, it's very easy to understand even within Newton gravity, but it's true in general relativity. If there is no mass, okay, it's analog of Euler's law, you know? Yeah. Gauss law, sorry. I confused Gauss with Euler. Okay. So there should be a question immediately appearing here. You see, independently of the radius of r of t, I have the same gravitational field outside. The same gravitational field outside. You see, I assume that there is a spherically symmetric collapse. So I didn't yet tell anything about the details. You see, there is a t minus here. There is different t for some reason. The same r. I didn't explain who is d omega squared. D omega squared is just the standard metric on the unit unit sphere. These are two spherical angles, theta and phi. So I'm going to explain the details what's going on and how this metric is glued to this through the shell, etc., etc. These all details will be given in a moment. Actually, this lecture is devoted to this background, to the discussion of the. Yeah.
Do we have any discontinuity?
Yeah, there is a discontinuity because stress energy tensor is proportional to the delta function r minus rt. It's like that. And you have to glue through it. So the second derivative of the metric is proportional to the delta function. First derivative has a jump. But the metric itself is continuous. Okay. This is stress energy tensor of the shell. Okay, one may ask a question. So I simplified the problem because usually the collapse is not spherically symmetric. But if the collapse is not spherically symmetric, the metric outside of the body is not like this. It's of course different. But far away, it again looks like this. But in any case, as you approach closer, you find a bigger and bigger difference from this metric because there are higher momenta present in the gravitational field. So, but if you have a spherically symmetric collapse, there are two advantageous things appearing. First of all, the metric is not always like this. Not only that the metric is like this, but also there is no gravitational radiation. There is no gravitational radiation. So the mass of the object throughout the collapse remains the same. Throughout all the time. Remains the same. This is of course a simplification. Why there is no gravitational radiation? This is again high school stuff. Do you know why one cannot construct antenna which is spherically symmetric and in all directions can detect the planes? You have to construct antennas which are directing either in that direction or in that direction or rotate, but they are flat. They're never spherically symmetric. You know why? That's a very simple question. If you have a spherical object which is electrically charged, independently of its radius, it creates a Coulomb field, which is Q. Q is the charge of this guy. Coulomb field outside of it. So electric field proportional to this, and magnetic field is equal to 0. So even if this guy will start oscillating, respecting spherical symmetry, it will always create these fields outside of it, and no electromagnetic radiation. That is because all the momenta, multiple momenta, with respect to the origin of this ball are 0, and no radiation. Of course, if you start to move this guy like this, it will radiate as a point-like charge. That's the reason when people create, how you call it, antennas, they have, how you call it, I forgot the name, even in Russian I forgot. Anyway, there are antennas like this. They should work coherently. And if coherently means that they oscillate with the same phase. It's exactly as if this plane moves like this. Huh? Dipoles, okay. No, I meant a bit different term, but dipoles is a good term. Фазированная решетка. Phase lattice, okay. Anyway, but if you create spherically symmetrical, it is exactly like this. So if the lattice is not completely spherically symmetric, it's only very, very high momenta is present. But the very high momentum radiation is very damped, so it doesn't work. Here the situation similar, but even stronger. To have a gravitational radiation, you have to have quadrupole moment, higher than dipole moment. So I consider idealistic situation, but actually I also can consider the situation that there is a gravitational radiation. You will see why. But I don't do that, but can. That's not very hard to extend. Anyway, so that's symmetric. Inside flat, outside Schwarzschild, independently whatever RT is given here. Now I find the following thing. Before t equals to 0, it's R0, and after t equals to 0, it's some R of t, which is found from the condition that it's a free fall. So it falls freely under its own gravitational field. So I will find this function. And that will allow me to find the relation between these two guys. So what should I do? First, metric is continuous, metric itself. It means that metric, this metric to this is, and this metric should be glued to each other at R equals R of t. You have to glue them to each other, make equivalent. First, let us do that for the case when the shell is static. When the shell is static. When the shell is static, so R is equal to R0, and I have to equate these two guys. It means that this is 0 because R is constant. This is 0 because R is constant. This R0 squared, so this guy equal to this guy, and you have to equate this guy to this guy. And you immediately find that dt minus is equivalent 1 minus Rg divided by R0 dt, square root. That's a relation between these two guys if the shell is static. So that's a relation between t minus and t before for t less than 0. Now, what happens if shell moves? If shell moves, the metric on the shell, let me make sure that I won't miss anything. Yeah. The metric on the shell itself, the metric on the shell, it means that it's d tau, this is a metric, three-dimensional metric. This is a metric on the shell, minus R of tau squared, d omega squared. This is proper time, tau is the proper time on the shell. So I have to equate this guy to this guy exactly at R equals to R of tau. That can be done only if you equate this guy. Here stands R of tau squared, so this guy is equivalent to this guy. Now you have to equate this sum of these two guys to this guy. That can be done only if dt minus over d tau squared minus R d tau squared is equal to 1. So what I did is just I put here R of tau divided by d tau and subtracted it. And to equate this to this, I have to have this. This gives me the relation between d tau and dt minus. Sorry, dt minus is equivalent to d tau square root of 1 plus R dot squared. You see here stands velocity, but there is plus sign here instead of minus sign. You are used to the fact that usually here stands minus sign, but the problem is that here stands proper time. That's the reason d tau, the plus here. It follows from this.
Where is Rg?
Not yet. I glued this to this. Now I'm going to glue this to this, the same. So you let me put this relation here. Before t equals to 0, T minus is the square root of 1 minus Rg divided by R0 T, right? I'm not lying to you. Yeah. Okay. Now exactly doing the same for this. So here, now for t greater than 0, I obtain that dt minus is equal d tau square root of 1 plus r dot squared. Here already I cannot put t minus equal to, because this is tau dependent. And now doing the same for this case, I obtain that 1 minus rg divided by r dt by d tau squared minus dr over d tau squared 1 minus rg divided by r equal to 1. So it's similar to this, but with this metric. This is the same d tau, proper time on the shell, the same as this one. So from here, I can find the relation. Okay, you will see. What will I find? Or I can write this as follows. Unfortunately, I cannot find from here simply the relation between r and, so I have two functions, tau, t of tau. This is a motion space-time world line or world surface. It's a world surface of the shell, world surface of the shell in this metric. I cannot find these two guys. I need extra relation, first of all, but also resolving is not that simple due to the presence of this guy. But as the collapse proceeds, R becomes closer and closer to Rg. So this guy goes to 0 as t goes to plus infinity, as the collapse proceeds. And then it's very easy to solve, because I can find the relation. So I find the approximate relation, 1 minus Rg divided by r. Here is squared. So I subtract the square, d tau over, I can write like this, dt, dr equal to dr, approximately. And this is easy to calculate. Because this guy is huge. I cannot drop derivative. Even if this is small, this can be very huge. Derivatives are never dropped off. This guy is just itself, without multiplying any function of tau which changes in time. Okay, this is very easy to calculate, and up to constants, it fixed. Integral is simple, it's logarithmic integral. Here I find the function between, the relation between r and t. R of t is approximately, looks like this. It's Rg, 1 plus R0 minus Rg divided by Rg exponent minus t divided by Rg. I fixed the constant of integration such that r at t equals to 0 is approximately equal R0. You see, I started, my shell at the beginning was very close to its Schwarzschild radius. So it's at very beginning already this relation was true. So I used it to fix the constant. So this is true approximately as t goes to plus infinity. Okay, let me fix that. Here.
How do you divide t over rg in the exponent?
What do you mean?
Well, exponent in the power of minus t over
Rg, it's dimensionless. C is equal to 1. Both are having, I measure time in meters. So I didn't yet find the relation between t and tau. This is remains to be found. But I found the relation between r and t. So the approximate motion, it's trajectory. One trajectory of the shell.
Can you try this solution when t equals 0? So you're right. Equals 0.
Yeah. This solution is, of course, is valid as t goes to plus infinity. But you see, I already started, at the very beginning, I said to you that my initial condition was that R0 minus Rg is much less than Rg. So it already was true, the relation. You see, this is exponentially damped factor. As t goes to infinity, this R of t becomes closer and closer to Rg. So the relation that R at R of t at any time minus Rg is much less than Rg is true. So I approximately use the fact that so I approximately use this expression also at t equals to 0. I can do that because of this condition. But it doesn't matter. Anyway, there will be a different constant standing here. Not much will be changed. I mean, if you want, I can put here C throughout my calculation. This constant is not very relevant. Now, what I see, the graph of this guy is the following. From the point of view of this metric, and this metric is seen by observers which are fixed above the black hole or above the shell. So I see the following situation. I see that there is this Rg, well, I don't see it, but I know that there is one. And it stood at R0, and then it becomes like this. Asymptotically approaching Rg, never crossing it. This is expression. So from the point of view of external observer, shell never crosses its gravitational radius. That's what I see from this calculation. Now, there is an assumption here, not very strong, that I assume that the shell very rapidly accelerate to the speed close to speed of light. From the point of view of the internal observer sitting here, shell very rapidly approaches speed of light. So dr over dt minus by modulus, because it's negative, approximately is equal to 1. Actually, I will call it nu, but I assume that this is, first of all, I assume that it is constant, and it's actually approximately 1, speed of light. That allows me to find the relation between r and t minus. So that will allow me to find the relation between t minus and t. That is important because I will match the frequencies. You will see that. I will have to find quantum field to perform quantum field calculation on top of this background. And for that, I will need to find the matching between times.
At this point, if R0 was very close to Rg at the beginning, how can you assume that the speed is close to the speed of light?
I mean, okay. Let me phrase it differently. then you will buy it. Again, you see, I don't need, this is an important point. Let me phrase it. It's a much stronger assumption that I phrased that I actually need. I need a weaker assumption. Weaker assumption I need for the following reason. You see, I need to know what happens to the background and to the quantum field on top of it at this stage and at the very final stage of the collapse. So at this moment and at this moment. I don't need what happens here. You will see why. This is not interesting times. In fact, the reason I told you that in my case, Rg remains constant. You see, there is no gravitational radiation, no loss of energy, so the mass of the shell remains the same throughout all its evolution. But I actually can relax this condition, can have at the beginning that it was spherically symmetric, but throughout the collapse at this stage, it was, I will, just a moment. It was fluctuating, creating radiation, etc., etc. So there was original mass, Rg0, and then it became Rg infinity, meaning that it was before, and t going to plus infinity. So it radiated some energy. But the point is that at the final stage of the collapse, shell, independently of whatever happened here, shell will become closer and closer to spherical symmetry. If it doesn't rotate, it will become closer and closer to be spherically symmetric. It is very hard to show that because you have to calculate what happens to multiple momenta. And you can show that multiple momenta die as time goes by. It's related to no-hair theorem. The multiple momenta die, and the shell becomes, if it doesn't rotate, it becomes closer and closer to be spherically symmetric with reduced mass because some of the energy is lost. So, in fact, using this ideology, I just need to know what happens to the background here and here. And as t goes to plus infinity, shell anyway accelerate to speed of light as seen by internal observer. Actually, I have plenty of time, so I'm ready to answer questions. Please interrupt me and ask questions. Okay, I was asked to... Let me just write here the following things, that I have ds minus squared and I have ds plus squared. And I'm working on gluing these to each other. I didn't yet use any of the property of the stress energy tensor. So I didn't use the fact that there is some stress energy tensor relating these two metrics between each other. So I'm gluing at this stage, I'm using at this, so far I'm using just the fact that two metrics are equivalent to each other at the shell, at the surface of the shell. I will use stress energy tensor when I will glue derivatives of the metric, first derivatives of the metric. Because that guy jumps on the shell exactly proportionally to the value of the energy stored inside the shell. And that's what defines Rg, this Rg. Okay, so far so good. I use this condition. This is approximately constant, and I assume that it is very close to 1. Yet I will keep it as nu. This is some velocity. That allows me to approximate that R of t minus is approximately R0 minus nu t. So it's approximately linear function. T minus, sorry. And that allows me to relate this to this and find the relation between t and t minus. This is highly important. This relation is actually the key point of the Hawking radiation. And it's related to the infrared shift from the, you know that if you create radiation very close to the shell, infrared shifts as exiting from here, and closer the source of the radiation, higher the infrared shift. And as the shell collapses, it becomes closer to RG, and you can put your source closer to RG, and closer source to RG, higher infrared shift, and as you put the source exactly on RG, infrared shift is infinite. So whatever fluctuation you create, it creates only stationary fields outside. Infrared shift is the following, I'll tell you. So if you create, if you have a source of radiation, suppose the dt is time with respect to, it's a time difference between two fluctuations. Bump, bump, tick, tock, time difference. If the metric is static, it comes here with the same dt, tick, tock, with the same dt. But the proper time here and proper time here are not the same, because proper time is g00 dt square root. This is the relation, this is the proper time for the static observer. So here d tau divided d tau, here will be 0, here will be first, d tau 0, square root of g00 at 0 point, d tau 1, square root of g00 at 1. And this is time independent, it's important. If it is time dependent, this relation becomes harder, and this relation becomes harder. If the observer moves, the time, proper time is also different from this one. This is if the observer stands. This is the proper time, definition of the proper time. Okay, but the frequency you measure here and here is exactly frequency is 1 over d tau. 1 over d tau. That's the reason frequencies at 0 and frequencies at 1 are related to each other. G001, G000. Is that right? Yeah. Actually, you can expand this. In Newton limit, G00 is approximately 1 minus TV, 2V. V is the Newton's potential. And you can find from here the work performed by the photon in exit in the gravitational field. So the closer you put this guy, smaller this guy is, because it's proportional to G00. Okay, you can perform yourself this very simple calculation. You have to just figure out what means proper time. That's it.
But how photons appear in this theory, which is classical?
Okay, electromagnetic radiation at given frequency. That's enough. For my discussion, is enough to have Zug, how you call it, wave packet of electromagnetic radiation with some, how you call it, intermediate frequency. The frequency will be shifted. There was no any H bar in my reasoning so far. Okay. Then relating this and this, equating to each other, I find that T minus is approximately R0 minus RG divided by nu 1 minus T RG. This is exactly the most important relation between this time and this time. Flat time and okay. Now, so far so good. Do you follow me? Didn't I lose you, more or less? I mean, if you don't have any questions, it means that you don't understand anything. Well, you had many questions so far. Okay. Anyway, now I am going to glue derivatives of the metric. To glue derivatives of the metric, I have to know differential geometry and Israel junction condition. That's too much time to explain, so I'll just give you the answer because it's very simple. The answer is extremely simple. If you do that gluing, you obtain the following thing, that Rg divided by 2 is equal to, I should use different, I hope, like this, m square root 1 plus r dot squared minus m 2r. That's very interesting thing. And the gluing condition assumes that this is equal to constant. So m is actually constant standing present in the stress energy tensor. Essentially, it would be a mass of the shell if there were not gravitational field. But this relation states the following thing. Here stands the total energy of the shell. Total energy of the shell is the sum of kinetic energy and gravitational energy. This is just Newton's, well, this is relativistic Newton's, and this is just Newton's energy. So it happens occasionally that almost Newton's mechanics you can use. Here is a plus sign because this is dot with respect to the proper time. You see the relation between, if you have a flat, well, it doesn't matter. Anyway, I will just make it worse if I'll start to explain this in greater detail. Actually, you can see here a very interesting thing. If Rg, I have to have that Rg is greater than 2m. If it is smaller than 2m, you have a bounce. You can find that this shell will be collapsing to some r, at which r dot is equal to 0, and then return back. From here, from this relation, you can find this is just solving, looking for this. If this is constant, this is energy conservation essentially. This is constant. You can find r as a function of t from here, and you can see that it will have bounce if this condition is violated. So I have to have this condition for the collapse to proceed. Anyway, this allows me to solve the problem completely. But I don't even need this condition. Because for me, for further calculations and discussions, for me it's sufficient to know this. If I glue derivatives of the metric across the shell using the jump where m defines the jump. M defines the jump of the metric because it follows from the stress energy. It's how we call it, a part of the stress energy tensor.
May I ask a question?
Yeah.
So if the energy is conservated, so your radiation flows from...
There is no radiation, as I told you. In spherically symmetric collapse, no radiation. When I talked about radiation, I added on top of the collapse some source, which creates some electromagnetic radiation going to infinity. Imagine.
We are going to get some Hawking radiation.
Yeah.
Where?
I have to quantize the quantum field on top of that. And of course, when I will discuss that, I will assume that there is no back reaction. I neglect the back reaction. The back reaction is weak.
So high energy is conserved.
So high energy is conserved, no quantum fields. It's all classical. Just classical gravitational collapse, no quantum fields on top of it yet.
Also, can I ask a question? What's the physical meaning of this condition? Rg greater than 2 masses?
I told you, if Rg is not greater than this, then I have a bounce. You can solve this equation, and you will see that it will bounce back. It will not collapse to create black hole.
I understand, but
What is the physical meaning? Not more than that. I cannot say more than that.
you said that M comes from stress energy tensor.
Yeah. But the total energy is not simply M. Total energy is also kinetic energy due to this M and gravitational energy due to this M. So it's more complicated object.
It is stress energy tensor of what?
Of the shell. It's similar to the point-like particle. You know how stress energy tensor of point-like particle is constructed? So it's similar to that. The only difference is not point-like, it's spherically symmetric, so it's similar to point-like particle in one dimension, where the one dimension is r, radius.
Could you repeat this? Why we need the dr dt minus equals 1, exactly 1?
You mean this? Why I need this to be close to 1? No, I don't need it. I just said that I assume that it very rapidly accelerates to the speed of light, and I need just this, linear law.
It's physical. This is physical assumption, or not?
Yeah, I motivated it. I know that it very rapidly soon accelerates to the speed of light.
Okay. This condition on derivatives satisfy on all time intervals.
Yeah, yeah. This is valid for all times.
No, I'm meaning that condition on derivatives.
Yeah, but this follows from the conditional derivatives.
We can equal the condition in infinity and
No, this relation has nothing to do with the condition on derivatives of the metric.
okay.
This follows from the conditional derivatives of the metric. And actually, in the future of in the rest of my talk, I don't need this. I just stress that what conditions it imposes, and what else? I don't remember. If I will need it at some point, I'll tell you. If I remember correctly, I don't need it.
Just let me check if I understand your flow right. So in principle,
So far, actually, this is textbook stuff. This you can find in many textbooks. Okay. Yeah.
so in principle, if you start with just a shell, then you write the equation of motion, and then you should obtain actually the metric inside and outside from the equation of motion. Right? But you are finding kind of shortcuts. So you kind of avoid these mathematical calculations, and you say, well,
Give you simple physical reasoning why it should be true. Yeah. Yeah. You can become way more rigorous than I am here, but that demands more time.
Sorry, at which point the black hole will appear?
That's exactly the point. The black hole appears when, actually, from the point. That's okay. Let's discuss that also. But that will. How much time do I have? 3 minutes?
No, 30.
30 minutes. 30 minutes. Can we put the Can we? No. That's important point. Actually, I can stop. I have last page for my talk here. Let's discuss that. That will be. I will share with you my opinion on what means creation of black hole. From the modern perspective, the black hole is actually this infinite free fall of the. So the star at some point lost its thermonuclear reactions are expired, thermonuclear fluid is expired, everything is burned out, no pressure, the star starts to collapse. From the modern perspective, black hole is just eternal collapse as all this matter approaches RG. In the similar manner, this is universal formula. So the matter consisting the star never crosses the RG from the point of of view of external observer. That's understanding from the modern perspective. From the point of view of proper time of the matter, if you fall together with the matter, you cross the horizon. So the creation of the horizon when this guy becomes Rg. This is time t minus. T minus is R0 minus Rg divided by nu. This is the time during which the black hole is created from the point of view. After this moment of time, the internal observer cannot escape to infinity, whatever he does.
But then there is no singularity,
No, singularity is created. From the point of view of this guy, it is created during finite.
Never approach Rg. So
Yeah, no. We will discuss that. That was the issue of my lectures during my, previous. Even if you use this reasoning, the singularity is there. If you draw the total space-time, singularity is created, it is present in total space-time. It's just observer dependent stuff what we are discussing. That observer sees that the matter approaches closer and closer, like torture becomes closer, slower and closer as it approaches Rg. You see this exponentially slowly approaches Rg as time goes by. It never, because these coordinates, this t and r in this metric, are defined only outside of Rg. So you have to use the coordinates which span all the space-time.
So when we look from outside.
Okay, let's discuss more relevant physical situation. I will explain to you in a moment. That actually black hole created within finite time. I just told repeated for you the textbook stuff now. People can tell you that people usually say the following thing. There is no device which can detect radiation with, any precision. Any device has a precision. As all the matter, this is Rg, as all the matter of the creating black hole approaches Rg, it creates radiation which becomes more and more infrared shifted, and sooner or later you don't see anything. That's it, you don't care. That's usual reasoning. Let me tell you my opinion. For that I have to draw a picture. Let me write the metric. The metric, Schwarzschild metric is as follows. This metric is defined for R greater than Rg. It's not valid for R less than Rg. But at R equals to Rg, this metric becomes degenerate, but this is a similar degeneration to the planar coordinates. If you have planar coordinates, for example, well, it's a bit stronger because this becomes 0, this becomes infinite. This is actually the problem because it's infinite. But here, this guy becomes 0 at r equals to 0. But this space-time doesn't have any problem at r equals to 0. This is just a problem of the coordinate system because at r equals to 0, phi is undefined. So somewhat similar happens here. Here a bit more complicated situation. But in any case, you can find a way to show that at r equals to Rg, there is a coordinate singularity. It's not physical singularity. So it's a problem of the metric. You cannot extend the metric beyond this point, but the space-time itself is well defined at this point, at this surface. So, for example, how to see that? You can see that by doing the following transformation. And define this at dr star. This is, I will need them. These are so-called tortoise coordinates. Then r star, you can integrate. So dr star is equal to dr 1 minus rg over r. And I can take the integral and fix some, how you call it, integrational constant. Then the answer will be like this. This is tortoise coordinate. I will use this coordinate. Actually, the rest of my talk today was this coordinate.
But for r equals 0, it's a real singularity, real physical singularity.
No, this metric cannot be used at r equals to 0. This metric cannot be used at r equals to 0.
But
This.
it's not a physical singularity.
You have to use different coordinate system where you can use r equals to 0. There will be different r.
As well as I remember, to extract the physical singularity, we can use some invariants such as Krishman invariant.
Yeah.
See that
Yeah.
infinity is
Yeah.
for r is equal to 0, but not on the horizon.
Yeah. Okay. Be careful when you say r equals to 0. This metric, I repeat, I already said it several times, but you yet continue saying that. This metric is valid when r is greater than rg. Rg is greater than 0. So this metric is not valid when r equals to 0. You can use this metric beyond the horizon, but there will be, so you can use this metric. Okay, let me do that also. You can use such a metric inside the horizon.
So what metric I can use
Oi, sorry.
r equals?
Just a second. Just a second.
Okay.
This metric looks very similar to Schwarzschild, but it's valid for r less than rg. It solves Einstein equations. It's not asymptotically flat. Here, time is not t, because you see the signature is such that time is this guy. And the metric is time dependent. What I did, I just flipped in this Schwarzschild metric, I just assumed that r greater than rg, and I flipped this, then the sign changed. All I did. So the singularity is at r bar equals to 0. Yeah. Yeah. Yeah.
So if you take any star, we can divide it into different shells, right?
Yeah.
And then follow your approach.
Yeah.
Then, if I understand right, inside the shell, the metric is flat.
Instead, no. If you have, how you call it? If you have such shells like this, the metric here, for example, is defined by this mass. It's not flat. It's not defined by outside shells, but inside shells curve the space-time. It's the same in Newton's gravity. In Newton's gravity also, if you are inside the Earth, the only thing there is this childhood problem that you have this, how you call it, elevator throughout the Earth, how it will go like this, and like, because how you call it, there is a if I correctly remember, there is an oscillatory, exactly oscillatory motion.
In the beginning of lecture, we use flat metric for r less than r.
Because I used, because Dima asked me about the ball which is filled in. I was discussing throughout this lecture thin shell, nothing inside.
Okay, nothing.
Looks like people are completely lost.
So nothing inside, but we use Schwarzschild outside.
Yeah.
So this ball must have a mass.
Yeah, sure. The shell has mass.
Oh, okay, okay.
The shell has a mass. Okay, now let me use, or I will use the following situation. So, so I have like this. And now, if I make coordinate change, I want to change from T, R. So here, essentially, I assume that R is a function of R star. So I have this metric depends on 4 coordinates. T, R star, theta, and phi. Now I want to change from T, R star to V, R. VR, where V is T plus R star. This is a coordinate change. This R coincides with the original R only for R greater than RG. This new R. So I make a coordinate change from this to this. And new R coincides with original R for R greater than RG. The metric after such a change, this is a change. So essentially I make this change. This is my change. Because the original metric is valid for this, I do this change in the original region, and I obtain the metric like this. 1 minus RG divided by R, dV squared. People will correct me. Minus 2 dV dr minus R squared d omega squared. Is that correct? I remember by heart. It's called by heart. It's called in-moving Eddington-Finkelstein coordinates. Is that correct? Who was checking? My students did the calculation. Okay. So now this metric doesn't have any problem. You see, there is no singularity. There is only this guy vanishing. When R equals to RG, this guy vanishing, but the metric is not diagonal, so it's not degenerate. You see that it's not diagonal. This is not diagonal term. As R equals to RG, I obtain the following. It's 0, 1, 1, 0, and here RG squared, RG squared sine squared theta. This is a matrix of the metric tensor at R equals to RG. This metric tensor is perfectly well defined. No singularity. So I can go with this metric beyond this region. So I extend my R to R less than RG. So it coincides with the original R at R greater than RG, and it's some new R inside R equals to RG. Maybe it's philological way of saying I can extend this metric to that region and consider it and use this coordinate system there, and I will find that at R equals to 0 there is a singularity, because the following invariant R mu nu alpha beta, R mu nu alpha beta is behaving like some inverse power. I don't remember the power. 4th or 6th? 4th power of this guy. Mm-hmm.
Why didn't we start it with just the Schwarzschild metric? Why we?
I started with Schwarzschild metric.
No, I mean, we started with the sphere.
Ah, that's exactly the point. Okay, that's a good point to finish my talk, because I will discuss. Can you remind me that I have to answer your question in 5 minutes? Now, using this coordinate system, I can draw geodesics, light-like geodesics. I will draw geodesics for which radially moving. So d theta is equal to d phi equal to 0. Radially moving geodesics. So I have V, I have R, I have RG, And light-like motion is when this equal to 0. This is the law of motion of light. Radial means that this is 0. Angles do not change. So you can solve. There are two equations, dv equals to 0 or 1 minus rg over r dv equals to dr, 2dr, sorry. And you could draw this, for example, these geodesics look like this. So V constant. And they, as t goes to plus infinity, because V is t plus r star, they go like this. And if you solve this, you find, for example, this is one of the geodesics. And as t goes to plus infinity, it has this direction. There are geodesics moving like this, and there are geodesics moving like this. And you have a clear separation. So these are in-moving geodesics. You see, if you, for example, at this point, what do you have? No angles means that you have a sphere of radius r, and you create two spherical light rays. One is ingoing, another one is outgoing. This is outgoing, this is ingoing. You see what I mean? At every point is like this. Now, so the outgoing geodesics are separated into two families. The outside family and inside family. The inside family, whatever happens goes to r equals to 0. So if you find yourself here at this point, you inevitably will move within this light cone. This is light cone. You inevitably end up at r equals to 0. Escaping r equals to 0 is the same as escaping next Saturday. Impossible. It happened. Unless Trump will do something. Okay. Oh, even if he will do, it will happen. Okay. This is one of the geodesics. So, for example, if you radiate a light being exactly at r equals to rg, it stays on this line. But you see, I drew this geodesics in the approximation that light rays, light zugs, light wave packet itself doesn't carry any energy. It moves along the geodesic only in this approximation. Of course, if the star is very huge, massive, you can neglect the curvature of the space-time due to these light rays. But the question is the following. Suppose you radiate a real light wave packet carrying energy at this point. Will it stay on this line? No, it will go either to this or to this. And that's exactly what happens. We see that, how you call it? We see that black hole is never created if we stay here. For example, we are fixed at some radius r0. Look, and something falls in. It emits radiation at equal distances, and it goes to you. You receive signals farther and farther, and when it crosses the horizon, it radiates a signal which goes parallel to you and never crosses you. That's exactly infinite moment of time. But in reality, it will radiate light wave packets, and they will be not staying exactly on this. It will either participate into creation of the black hole, or will escape to infinity, and you will receive the last wave packet. And then you will not receive anything after that. That's a moment of the creation of the black hole. But the problem is that then this moment is defined by the energy of the last zug. You see? So it's not exactly Rg. It's at some point Rg plus energy of the last zug. That's not quite, how you call it, universal definition. But in reality, when you will measure radiation, and if you have a very strong device detecting very tiny radiation, you will receive last zug. And after that, there will not be anything. So that's my understanding. Now to your question. So what you asked, why we started with the black hole. with the star, not the Schwarzschild. So now I will essentially tell you what I'm going to talk in the next lecture, or sketch the idea. The point is that you have to quantize, so you have to quantize some field on top of this. I will be quantizing the scalar field with the Lagrangian like this. D mu squared, square root of modulus of G. My signature is minus, so it's minus m squared phi squared. So I will quantize square root of, I will quantize this field. To quantize it, I will have to find H0, Hamiltonian, free Hamiltonian. If I use Schwarzschild, free Hamiltonian will be sum of k, omega k, ak, dagger ak. So it's diagonal. And if I calculate stress energy tensor, it will be 0 for eternal black hole. Exactly due to the point that I have modes which are, they are bounded from below. So k is greater than 0, greater than actually. In reality, it's omega, 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 and omega is greater than m. M is the mass of this field. And stress energy tensor will be 0. No radiation. Although people will tell you in the textbooks that there is a radiation in the eternal Schwarzschild, etc., this picture. The problem is that you can specify different ways of definition. You see, there is this state here with respect to I average. I can define this state such that there will be radiation. It's called unruh state. I can define state such that the radiation will not be 0. I can define such that it will be 0, depending on which state I use. And if I have a situation that I am considering, I don't have any ambiguity. Before the start of the collapse, I have a clear definition of what means particle, of what means vacuum. So I use vacuum state before the start of the collapse. But yet, even if I started with the vacuum before the start of the collapse, as t goes to infinity, I will have non-zero. And that is because my Hamiltonian will be much more complicated than this one. Okay, that's the reason I am considering collapsing background. Actually, if you look for the original paper of Hawking, he considers collapse process to define his. And then people already started, and he himself started to discuss various occasions without completely properly and correctly defining conditions under which his calculation is valid. Okay, that's it. I can stop here, so you can ask questions.
So you say in classical picture, where there is pair production near the horizon, you cannot calculate correction. Which correction you mean, QED or?
Quantum field theory. Quantum field theory corrections. Well, any corrections, because you see, to me, physics is when not simply you perform a mathematical calculation, but also you specify under what conditions this calculation is valid. Of course, in ideal situation, you should phrase all the possible assumptions, but that's impossible. All possible, you always make some assumptions, sometimes hidden assumptions. So, but in that calculation, I actually give it, I can give it to you. I don't want, because my students which are working in the group with me, they have to perform it themselves. I don't want to show them the calculation. It's very simple. It's a third-year student can do the calculation. Who knows quantum mechanics, semi-classical approximation, they can do that calculation for that picture with two pairs. But, and you will also eventually find loopholes in the calculation, because it's a single particle problem. Single particle problem doesn't give you, to have this, to make the proper calculation, you have to have multiple particle calculation, many particle calculation, quantum field theory calculation, not single particle calculation.
Is I proper understand that, for example, we can calculate the Casimir energy before starting the collapse? And for example,
Not Casimir energy. Don't I won't calculate T00. Casimir energy is T00. I will calculate TR
but will it do
1, 0.
before the collapse and
Yeah, before the collapse, it will be 0.
in Casimir energy of this field,
Casimir will it change?
it will change.
Probably yes.
It will change
Because there is amplification of 0 point flux. You see Casimir energy in the calculation of this guy, you use the modes. Modes are not simple exponents. Huh? Sure? Yeah. It's not the, but this guy before the collapse and the final stage of the collapse will not be the same.
So it means that this energy of vacuum changes for defined, for finite time minus, yes? Which is equal to R0 minus Rg.
I calculate this guy in outside metric. I didn't calculate it inside the shell. I don't think that it will, if you remain, or if you see there is this moment when this becomes 0. If I calculate before this moment, if my T minus is less than R0 divided by nu, and I am inside the shell, I think my T00 will be the same as in flat space.
Yes, you're right. But outside it changes.
Outside changes. It's a function, both this and this function of R.
And these changes of energy can flow out from the star, like a radiation, for example, because it will emit.
First of all, I will see the radiation. I will see the radiation, this guy, and moreover, my stress energy tensor will be this expectation value obeys this condition, conservation condition. And I will see the radiation. But if it is it related to the fact that this guy is changing in time and as a function of R? Maybe I can trace that from that. I didn't do that tracing, but maybe I can trace that.
It's like a dynamic Casimir effect when your mirror.
Some people say that black hole radiation is similar to the dynamical Casimir effect. And actually, loop corrections to the dynamical Casimir effect are also worth to find. People don't look for them, and they are very important.